So next, we have Francesca Mignacco, who's a final year PhD student at Institut de Physique Théorique of Université de Paris-Saclay. And Francesca is going to be explaining us a little bit how ideas from physics can bring insights about stochastic gradient descent and optimization landscapes. So when everything is set up, the floor is yours, Francesca.
Thank you. Okay, hello everyone. Thank you for the introduction, and thanks Giulio for the very nice talk. Today I would like to talk to you about what statistical physics has to say about learning in very high dimensions, and in particular concerning how to track the trajectory of stochastic gradient descent algorithm. So before, I just wanted to list a few of still open questions in the field in general of deep learning theory. So for instance, what theoreticians would be interested in understanding is why heavily parameterized neural networks still do not occur in overfitting, or what is the effective number of parameters to be learned, and why learning algorithms trained with backpropagation do not go for poor generalization, but instead perform well also on previously unseen data, and what is the optimal stopping time for the algorithm. So these are all questions that are still being asked, but are actually quite old. They are from 95, I would split them in two types of questions. So the first two are concerning what I will call static properties, in the sense that these questions can be tackled by fixing the training at a certain time, usually at the very end where the network has already been learned, and analyzing what is the final generalization error as a function of the problem hyperparameters. While the second set of questions are more intrinsically dynamical, in the sense that they are really related to the optimization strategy that is used and to the time evolution of the algorithm. And I will focus more on the second type of questions. So I'm very happy that Giulio mentioned this at the end of his talk. Indeed, it's very important in order to say something about the principles that underlie learning. It's very important to understand the interplay between these three ingredients, so the structure in the data and the architecture that we have already heard of a bit, and also how the optimization algorithm enters. And both like understanding each of these components separately and their interplay will hopefully lead to a more complete theoretical understanding. And in this talk I will focus more on the optimization strategy, which is where most of my work focused. And just before, I want to give you a bit an idea of the setting and the approach that I will take, which is more like a la physicist. So physicists are usually interested when systems of a large number of degrees of freedoms are concerned, are interested in computing the average behavior of the system. So in general, the problem that we will have is given some training data and the corresponding labels that are sampled from some given distribution. We want to learn a predictor of a previously unseen data point, and this predictor will be parameterized by some weights that will be computed via the minimization of an empirical risk, which is given simply by the summation over all the available data of some loss that accounts for the performance on each of the training data, and some regularization can be added. And the theoretical questions that are typically asked concern the predictor's error. So we would be interested in understanding and predicting what the error will be. And there are two types of errors. The generalization error, which is the one on the test set, so averaged over the data distribution, and the training error, which is the one that we actually have access to, which is just empirical average over the training set. And in particular, one is interested to assessing the difference between these two in order to be able to tell how good will our prediction be in practice. And this has been widely studied in statistical learning theory, and a common approach is deriving bounds. But it has been shown in some cases, for instance, for the model that I will explain soon, that sometimes the difference between what these bounds predict and the actual behavior that is observed on average can be quite large. So, for instance, this is a model that I will consider throughout the talk. It's called the teacher-student model, where the data is simply Gaussian, generated by a standard Gaussian, and the labels are generated by some unknown teacher vector. And the task is to learn this teacher vector by a student network. And in this setting, it has been shown that by Ibarra and co-authors that the bounds, some of the bounds, for instance, the Rademacher bound that basically measures the complexity of the hypothesis class given by the predictor, is actually quite far from the actual performance that is assessed in practice by the network. So this is an example where, while the worst case performs quite badly, actually the typical performance, for instance, in this case of logistic regression on a classification task, can go even very, very close to the optimal one, as was shown by Aubin et al. So this is why we are interested in understanding the typical case performance and computing these quantities, so the errors, training and test error, as a function of some of the, for instance, in this case, the sample complexity, that is the fraction of samples over the number of dimensions. So as I said, I will focus on the optimization algorithm, and I will try to study the dynamics of learning with the gradient-based algorithm, and in particular stochastic gradient descent. And the aim is to try to devise some simple model that is yet expressive enough to capture at least some of the phenomena that are observed in practice. And so it's still able to tell us something about the phenomena that are observed. And so I will have to resort to some simplifications. First, I will consider no particular architecture and a single layer neural network. And also, regarding the data, I want to simplify my life as much as possible. And in this case, data scientists and physics agree that the best thing to do is to take the data as Gaussian, as I said. And I will focus on the optimization algorithm. And even with these many simplifications, yet there are still many open questions regarding the optimizations of stochastic gradient descent. And so what I will consider is a dynamics where where the weights at each time are updated in the direction of the gradients of the loss, so the direction that minimizes the loss. But since computing all the gradients at each time, it's quite expensive, since typically the training set is very large, I will just focus on mini batch gradient descent, that I will also call stochastic gradient descent during the talk, where only a fraction of samples are selected at each time, and these are given by the indices selected in this mini batch, and which changes over time. So in practice, my weights will be initialized in some random position, typically high in the loss landscape. Then at each time step, I will draw a mini batch and I will update the losses. Then the mini batch will be shifted, and so on and so forth. And what is surprising about this procedure is that it leads to good minima in terms of the generalization performance. So this algorithm is efficient not only in terms of computational cost, but also in terms of performance. And this is not trivial at all. Indeed, it has been shown that there exist regions of the loss that are very bad and that can even be reached dynamically if the algorithm is initialized in a very adversarial way. But in practice, with the random initializations, they are not reached, and actually the regions that are reached are good. So there are a lot of open questions on which basins are attractive, what is the role of this very specific noise structure, and also in which cases is this procedure really better than its deterministic counterpart, so with the full batch gradient descent, and in which other cases it's only faster, but in principle it's not really better. In order to answer all these questions in practice, what we need to do is to find a way to model the dynamics of a mini batch gradient descent. And this is not trivial because this noise has a very particular structure, and it drives the dynamics out of equilibrium. And this modeling has been done in using different strategies. A series of works did this with some approximations on the noise introduced. So again, this is the dynamics of the weights given the loss, and this nabla tilde is the approximated gradient. These approximations basically see the stochastic gradient descent algorithm as a Langevin-like process where the difference between the full and the approximated gradient is invoking the central limit theorem considered as Gaussian noise. And then another series of works questioned the validity of the central limit theorem in this setting, and instead showing that in some cases the dynamics of stochastic gradient descent can be characterized by big jumps, and so they use Levy process to model these dynamics. While the perspective that I want to consider is a bit complementary, so I do not want to assume any approximations on the process, and I want to try to track the whole learning trajectory of the algorithm. And this has also been done in some specific cases, for instance, for the deterministic dynamics of gradient descent in linear networks, also in deep linear networks, and in many cases for online stochastic gradient descent, so where basically a new sample is used at each time to update the weights and is never used again. But in this setting, there is no real distinction between a train and test, and there is no notion of landscape, so one cannot really study the gap between training and test error. But still, this yield very interesting results, for instance, for two-layer neural networks. So in this case, a bit more complicated architectures can be considered. There have been a lot of works considering two-layer architectures with a finite number of hidden units, and also in the so-called mean field limit, where the size of the hidden layer tends to infinity. While in my case, what I will consider is the dynamics of multipass stochastic gradient descent, where the samples are reused multiple times, and for, as I said, a single layer neural network. And the key ingredients of this approach are that I will assume a generative model for the data because I'm interested in the average case scenario, so I won't compute averages. And the thermodynamic limit, so the infinite dimensional limit, where both the number of samples and the number of dimensions go to infinity at a fixed rate. And what I will present is based on some works that I did with my supervisors Francesca Mignacco and with Florent Zakala here at IPFL. So just to fix the ideas of what I mean by mini batch sampling, I will have to consider a protocol, and this protocol will crucially change the type of noise that is induced in the dynamics. So for the mini batch drawing, I will first consider vanilla SGD, which is basically sampling with replacement at each time step by fixing the fraction of samples that are in the mini batch. And the other process that I will consider, I will call it persistent SGD. It's not what is done in practice. We have introduced this. And basically the difference is that in this case, the samples that are used for learning are endowed with some persistence. So instead of drawing from scratch the samples at each time, each sample persists in the training mini batch for some characteristic time, and independently, so independently all of the samples undergo this two-state Markov process characterized by some rates, and we will have to fix this persistence time. So after all these introductions, what we managed to do is that we were able to write analytic equations that can fully track the dynamics of this algorithm in this simple setting, but within this simple setting without resorting to approximations on the dynamics of the algorithm. And basically this, we use this dynamical mean field theory from statistical physics that allows us to start from the very high dimensional system of the gradient descent dynamics, so the dynamics of the weights that are infinitely many and are strongly correlated, and we end up with just the dynamics of one effective stochastic process that captures basically the projection of our weights onto the noise that is in the data, and also one ODE for this parameter M magnetization that tracks basically the projection of our weights onto the signal that is in our data. And I will not have specified the data is some Gaussian plus some signal, Gaussian noise plus some signal that I will specify later, but this is actually quite general with this range of simple models for single layer neural networks. And what I'm hiding a bit the complexity of this procedure, which is mainly numerical, because this set of equations actually depends on some kernels and auxiliary functions that in turn are averages over these processes. So in practice, the procedure to solve this is numerical and must be done in a self-consistent way until convergence of the equations. And actually, I will show you that this leads to very good predictions. So I will have now to fix some data model. So first, I will consider binary Gaussian mixture classification, where our data is drawn by a binary mixture of Gaussians, and the goal is to learn the best separating hyperplane for these two data, for these two Gaussian clouds. And we find that our theory is able to predict very well the simulations on this model, even if they are done for dimension that is few hundreds, and our theory is infinite dimensional, both for the vanilla stochastic gradient descent and the persistent algorithm for different values of parameters. So here I'm showing, for instance, the generalization error as a function of time, and the dots are the simulations, and the lines are our theory. And what we can also do with this theory is that we can try to characterize a bit better the noise, the effective noise that is introduced by the stochastic gradient descent algorithm. So we know that if our dynamics was at equilibrium, and if we could access the linear response to an infinitesimal perturbation of our weights and the correlation of between our weights at different times, this would be related by the fluctuation dissipation theorem, and the slope of this linear relation would be given by the temperature of the system. However, there is no temperature in this case. Our noise is much more complicated. We're not injecting any temperature in the system. There is no bath. But actually, these two quantities and also some integration and rescaling of these quantities are directly available from dynamical mean field theory. for the stochastic gradient descent algorithm. So we can plot, we can do a parametric plot of these two quantities, and we can see that actually the relation is linear. So we can extract an effective temperature that is associated to the dynamics of stochastic gradient descent, and as it has been done for other physical systems, for instance in active matter, it is basically a measure of the magnitude of the noise that is introduced by the algorithm, and we can compute the dependence of this effective temperature on the problem parameters. So, for instance, we can see that it is increasing with the time step dt, and that it is non-monotonic with the batch size that we use. And also, if we consider the persistent stochastic gradient descent, we also have that here the temperature depends on the batch size in a non-monotonic way, and if we consider the persistence time, we see that it is instead increasing the more and more persistence we introduce in the system. So this was a very simple model that allowed us to derive the theory and allows us to characterize the noise in a setting where, since the problem is convex, there is really no other source of noise than the algorithm, because the landscape, again, is convex. And so we were able to extract all these properties, but we were not able to answer the question regarding the performance and the comparison between stochastic gradient descent and gradient descent, because the previous problem was so simple that basically the performance was good in any case. So we said, okay, let's consider this question on whether the stochasticity is beneficial by taking an intrinsically hard problem and seeing whether at least, if it at least in this very hard setting, we can see an advantage of the stochastic noise. And so we took as an example of a hard problem, the sign retrieval problem, which is again another type of, which is again a teacher-student problem, where so the data is Gaussian, and the labels are generated as the scalar product between the data and the teacher, and the activation function is the absolute value. So basically, it would be simply a linear regression if we knew the signs, which we don't, and which complicates the problem a lot. So the landscape of this problem is highly non-convex and has a proliferation of local minima, which can make the life of a gradient descent very hard. And so we compared our three algorithms in this setting, where the performance in this case is measured as the cosine similarity between the estimated weights and the teacher weights. And we see that both gradient descent and stochastic gradient descent get stuck in local minima, while quite surprisingly, the persistent stochastic gradient descent algorithm can really jump onto the signal and achieve perfect recovery. So this was quite interesting, first showing that the noise has a crucial effect in these dynamics, and secondly, that the persistence plays a non-trivial role. And to look at it more closely, these are all results from simulations where we see again the magnetization or cosine similarity as a function of time for different instances of the algorithm. And here I am starting by, I'm not starting from 0 for the cosine similarity, because we were interested in the perfect recovery. And so we consider informed initialization, and we also consider macroscopic initializations as a way to probe the landscape closer and closer to the signal. And we can see that even if we start macroscopically close to the signal, the gradient descent dynamics can be trapped in local minima, and so it's characterized by very long plateaus and then sudden jumps. This is also the case for the vanilla stochastic gradient descent algorithm, even if a bit less. While the persistent SGD displays basically no plateaus, apart from the first one, which is proportional to the persistence time, because basically before the persistence time, effectively the batch has not changed yet fully on average. While after this time, the algorithm goes on the signal. So this shows that the noise induced by the stochastic gradient descent self-anneals during the dynamics. And indeed, this would lead to an effectively zero temperature at the end of the training when the signal is reached. Again, we could compute theoretically the prediction of these learning curves. So here we have that the theory is in red and the simulations are in gray. And we have that, again, even though the simulations are at finite size, the match is quite good. And this is also a guarantee that the role played by finite size effects in what we see is not crucial, since our theory that is in infinite dimension can really match these simulations. So this is what I had to say about what we studied on the dynamics of learning for simple data, for a very simple data model, the teacher-student model. And I just wanted to mention that there is a lot of work that has been done in the direction of complicating the data structure model. Also, like a first, like a quite smart way of complicating but still keeping the teacher-student model can lead to very good results in terms of characterizing the data structure. And I just wanted to mention this example. So basically, this is a work by Bruno and co-authors, and they show that if we take a teacher-student model, but where the teacher and the student are allowed to act on different subspaces. So we basically have these two vectors that are jointly Gaussian, that are correlated, and one is used by the teacher to generate the labels, while the student network is handed the other one and can act only on this to learn the predictor. With this generalized version of the teacher-student model, one can already track the performance of more complicated data structure, for instance, where the data are generated by a GAN and learned by a two-layer neural network, or even for real data from Fashion MNIST. So this is just to say that there are a lot of open directions and open questions, both on how to characterize the noise, so how to study more the interplay between the noise and the landscape and link this to the generalization. So how to study what happens when the effective temperature goes to actually zero, and so when the dynamics stops and where it stops. So how can we have an alternative characterization of the noise in the regions of zero temperature? And how can we merge this formalism with more complicated data models or optimization strategies? And this is what I wanted to tell you, and thank you for your attention.
Thank you, Francesca, for the very interesting talk. Do we have any questions? Yeah, there.
So, yeah, I have a question. Okay, I have two questions, but they are related. So how big are these models in general? Like how many neurons you have in this kind of networks that you are dealing with? And based on that, I wanted to ask you if it would be feasible to compare the persistent stochastic gradient descent, not with gradient descent, but maybe with something like more powerful, like this limited memory BFGS, which are these algorithms that use also Hessian information, so they somehow estimate also the curvature of the data set, because maybe then could see if your algorithm is using some kind of curvature information from somewhere.
Okay. For what concerns the number of hidden units, is one. We have one neuron because the model is a perceptron. But it is possible to, and so this was why I said that there is no architecture actually. We can derive the same results for networks with few hidden units. So while considering the number of training samples and dimensions that are infinite, while taking the hidden units of order 1. And for what concerns the curvature information, it's actually very interesting. So for what concerns the modeling of these types of dynamics, I am not sure that it can be done, but one can try to think on how to also track these dynamics with the theory. And it would be interesting also to connect it to the effective temperature in terms of what information it gives about the curvature of the loss. Because indeed, okay, I don't know if this, I haven't thought about this, but since we see that the effective temperature is increasing with the persistence time, one could maybe link this to effectively increasing the curvature. I don't know, but one can maybe put this in relation.
Thanks.
Do you think you have a method to generalize the effective temperature to other models?
Like what type of models?
I mean, you said no architecture here, but any architecture, any other optimizer?
Yes. Okay. So for the architecture, as I said, that there is work that is been done in this direction, but the bottleneck is that for the moment, I would know how to write these equations for a few hidden units, not more. Although there are for the phase sign retrieval problem, for instance, there are results that concern the gradient descent with an infinite number of hidden units, and in that case, it has been shown by Mannelli et al. That it becomes much easier to retrieve the signal even at finite sample complexity. So somehow it's true that it's interesting to studying the interplay between this persistence and in analogy with adding more hidden units, for instance, because they both seem to simplify the problem. For what concerns the optimizers, it has been done for another problem, an inference problem. That's called the 2+P spin model. That the dynamics has been studied with dynamical mean field theory and the momentum, so optimization with momentum. So, for instance, this is something that could be analyzed by this theory. And for what concerns the data, I am more optimistic that there is a lot of room for work in that sense, because it has been done a lot of work for the static computation. So, for instance, characterizing the asymptotic performance of some networks that are close to this, but with much more complicated data structure. And I'm quite confident that in some cases, at least at an heuristic level of computation, these two methods can be combined to study dynamics of learning with more structured data.
Thank you very much.
Any other question?
Thank you. Thank you for a very insightful talk and a great literature review. So I was just being curious, when you used mean field theory to go from like an intractable, a pretty complex equation on W to, you had a nice equation for, I think, H and M,
Yes.
the evolution of H and M. And I was just trying to get some intuition on memory term.
Yes.
So everything that's behind the integral. So what can we learn from that? Does that tell you like how the learning rate evolves as a function of the trajectory, like how the autocorrelation in time?
Okay, in this case, okay, the big issue of this is that indeed in the dimensional reduction you add a lot of memory terms, and And then, okay, the learning rate, here we do not consider any learning rate annealing schedules. I don't know if here the learning rate is fixed in the dynamics, in the iterative algorithm. Then the equations are derived in continuous time, where this continuous time limit is well defined because of the persistence term that we have that allows to define the limit of the algorithm in continuous time limit. And then when we solve these equations numerically, we discretize them and we match the time discretization that we use to solve the numerics with Euler method to the one that we use in the update of the algorithm. And in this case, we can reconstruct the curves quite well. So, but we haven't done a study of learning rate annealing schedule. Then you can, in the stationary state, you can look, for instance, at how the kernels decayed to see what is for instance, you can see that persistence adds some longer time correlations in the stationary states between two times. And here, and you can see that also from the effective temperature that is actually also dependent on the persistence time. But in general, yes, these are quite complicated to solve for very large times. So if it's only, to get information on the stationary state and on the long time behavior of the kernels, you need to integrate them for very long times, and I'm not always able to do that.
Sorry, just as a quick follow-up, does that mean that that H equation tells me something about how the weights evolve and the
no, sorry. The H, sorry, yes, because I didn't say that then all the quantities of interest that are the performance, so the errors, the loss, and the accuracy and all the quantities are just a function of these two parameters and the norm that can be tracked. So basically by constructing these few variables of interest that are how the weights interact with the data, then you can track all the, because of concentration properties in high dimension, then the loss and the errors only depend on this.
Okay, thanks.
So maybe a silly question. So in this non-convex problem, the persistent SGD performs very well at escaping from local minima, spurious minima. How does it perform in practice, actually? If you just run this for a data set, does it actually is better? Is there any drawback in using this as an actual algorithm?
Realistic data sets.
Yeah, if I take your word and say, okay, it's good for non-convex problems, I'm just going to try a neural network with that.
Well, this is it's important to keep in mind that this landscape, it's not really the typical landscape where neural networks are. This is an inference problem that is very hard, while typically, where there is just one global minimum, that is the signal, and then there are all local minima at higher energy. While typically in neural networks, there are very large basin of solutions that are flat and wide, that are more like these seas of solutions. So I think that in practice, for typical learning tasks, so I don't know, image classification, you would not see a clear advantage of persistent. I have not checked this very consistently, but for I don't know, other types of problems with this, where this type of landscape have to be considered, maybe then there is an advantage.
Thank you. Let's thank Francesca again for